Hi, so today we are looking at an interesting problem. So it's from CodeJam 2010, and it's from the qualification round. It's called Snapper Chain. I will um, I will put a link to the problem in the description, so you can take a look. It's a little bit hard to understand, so read it carefully. I would suggest and come back here. So I'll explain it a little bit. So what is the problem? So it consists of having a snapper, which is just a device that that has like that has two sides. So on one side you would have an input plug and into an output socket, and on the other side you would have an output socket that you can plug a light or another device into. So you can imagine it like something like this. This is really just an illustration where you have the input here, where you plug it just into a socket. So you can imagine here there is a socket here, and you have an output here to which you can plug either a light or a device. So either light or a device. So you can have, let's say we can have another device, another snapper S2. Let's say we have another one until the last snapper device, and this one has, let's say, a light plugged into it. So this is the logic of the device. And this device here, this snapper device, has these types of states. So it has different types of states. So it can be either on or off. And it can also be powered on or powered. That means that if you plug the light into it, the light will be on, and it has a not powered state. We will see in a second why does that matter. Okay. And here the problem says that we have n snappers or snapper devices that are chained together in this way here, and okay, and let's see. So the light is plugged into the nth snapper, as I said. So the light here is plugged into the nth snapper, and the initial state is that all these snappers are off. So their state is off, all of them at the initial state, at the initial step. So let's see. So step 1, like here, let's say we have S1, S2, Sn, and all of them are off. Let's represent on by 1 and off by 0. So initially we would have this one be 0, this one 0, and this one 0. So all of them are off first. This is the first step. And then step 2, what happens? And only, so I forgot to mention another detail. So initially all of them are off, but also S1 is powered with the socket that we described earlier. And you can, like, the user is, or this problem consists of a user that snaps his finger, that can snap his finger, and when he snaps his finger, he makes a clicking sound, and any snapper, one of these devices that receives that there is receiving power at that time of the snap can toggles between on and off. Okay, so let's write that here. So after a snap, like a snapping of fingers, SI, if powered, can toggle its state. On and off. Which means that if the user snaps and the snapper is powered, then its state, if its state is on, then it switches to off, and if its state is off, it switches to on. Now let's look at step 2 here. So we described step 1 where all of them are off. Step 2 happens when, so step 2 when the snaps, so every step here the user just snaps. So let's call it instead snap 1. So here what happens is snap 1. And here what happens is snap 2. Okay. So in the second time the user snaps his fingers, it toggles both snappers and then cuts power from the second one, but leaves it in the on state but with no power. That means that the next time the user snap, that value will not change. So what happens in the second step? So let's draw our S1 here, S2, this one receiving power, and we would have Sn. Let's just increase this, add S3 to be able to see more. Okay, so what would happen in this case? So it toggles both snappers and then promptly cuts power. That means sorry, this is the initial step, like this is step 0. Step 0 is when all of them are off, but step 1 is when the first snapper gets to be on the on state. So when the user snaps first his finger, this one gets the on state, so 1. So the second snap toggles both snappers and then promptly cuts power off from the second one. So that means that this one, which was on, when we toggle it, it is powered, so we can toggle its state. And so that means that its state now becomes 0, it's off. State of the second one becomes 1, but it is no longer powered. And then the rest stays 0. Okay. And then on the third snap, what happens? So the light is plugged here, we should not forget that. And so on the third snap, it toggles the first snapper again and gives power to the second one. So that means this one is toggled again and gives power to the second one. Now both snappers are in the on state, so this one becomes on. So toggles the first snapper again and gives power to the second one. So this one becomes powered. So the snap didn't put this off because it wasn't powered first, so we didn't change its state. So now both of them are in the on state. And if the light were connected to S2, it would be on, but if it's connected to like another one that has 0, it will not be on. The light itself will not be on. And so here we will keep having zeros. And it will continue like this, in this manner. Okay. And after that third snap, the user just continues doing this for hours, and the question is will the light be on or off? Be on or off if after like k snaps. After k snaps. And remember the condition that light is on only if it's receiving power from the snapper it's plugged into. So if we go back here, a light here is on only if it's receiving power from the snapper it's connected to. And this one is giving power to this light here only if it's 1 and it's powered. Okay. So this state here and this state here, not this state at all. Okay. So let's continue this and let's draw some examples and just see how this works. And so the input to the problem that we get is we get n and we get k, which are the values here for so n is, this one is the number of snappers, sorry. So this one is the number of snappers, and this one is the number of snaps. So this is the number of devices, and this is the number of times the user snaps his fingers. And this is the input that we are given. So it's useful to look at some examples just to get a handle on what's happening. So let's pick the first example where k is equal to just like, let's say first n, let's pick n to be just 2, or let's just pick the smallest one, n to be 1 and k to be 0, which means we have one device and k and 0 snaps. That means that we have just one device which is initially set to 0, and that's about it basically. And that means that the light is plugged to this device, which means that in this case we get, what is the answer here? The light would be off, so the answer is off. Now if for the case where n is equal to 1 and k is equal to 1, so the initial state is this one, but the second state would be S1, where we toggle it to be on. And since the light is plugged to this, and this one is powered with the socket, that means that our answer is on. Let's look at another case where n is 2. N is let's look at where n is 2 and k is, let's say, just 1, and go from there. So in this case what would happen is we would have S1, S2, and so the number of snaps is just 1, so this one keeps being is 1 and this one is 0, and since the light is plugged to this one, this would be off. The second step, let's say if n is equal to 2 and we snap, the user snaps 2 times. That means that S1 is 1. That's the first step. And then in the second step, what happens is this is powered to socket, this one becomes 1. And the light is plugged to this one, and since S2 is powered, and it's why is it powered? Because it's plugged to S1, which has power because it's coming from the socket, and we didn't run the third step here where we didn't do a second snap here. So we did a first snap. But the second one is not powered, right? So S2 is not powered here. We almost made a mistake. So S2 is not powered because after we toggle S1 and toggle S2, we put S2 to not be powered. So my answer here is actually wrong. So this one is not powered. Only if we go here and we do n equal to 3. Let's say n equal to 2 and k equal to 3. In this case, we get S1. Actually, in the second step, I forgot to do this. So here it's 0. It becomes 0. If we take a look at what happens here, S1 is toggled back to 0. And so 0, and this one is not powered, and so off. Now the case where we have 3 snaps, so which means after this step here, what do we get? We get S1 to be, let's look back at third snap. So S1 becomes 1, and this one becomes 1. So we would have 1, 1. So 1. S2 becomes 1 and is powered now. And the light is plugged into this. And since S2 is powered, L now is powered, so the light is on. So this is a really cool distinction. We will do another example to see it clearly on n equal to 3, but you can see here that this is for n equal to 2. For n equal to 1, we have 0 and 1. So we have like the binary permutations for size 1. So 0 and 1. For 2, we have the binary representation for just 2 binary numbers. So 1 0 first, and then 0 1, and then we have 1 1, and don't forget we have also 0 0 state. Okay. Let's continue and see if this applies also to this realization that we had here applies also for n equal to 3 and k equal to 3. So here we were at. So let's go here. Let's see step 1. Like instead the snap 1. So snap 0, like just initial state, what would happen? Would have S0, S1, S2, and S3, and the light is plugged here. So in this case, all of them are zeros. And the sect is plugged here. The second case where snap is 1, we get S0, S1, S2, and the light is plugged here. And now we plug this on, and then snap 2 happens. And so in this case, we have S0, S1, S2, S3. And so what happens here is that this one is 0, this one becomes 1, but it is toggled on, but it's made like right away, it's made not powered. and this one is 0, and this one is 0, as we can see here from the problem description. So 0, and this one becomes not powered. After that we power it on and we switch S1 back. So that means snap 3. We can see here we get S0, S1, S2, S3, and the light is plugged here. And here we get 0, we get 1, so this one is toggled on again. And this one is, the second one is made powered. Yeah, not sure why I did here S0. Sorry. Yeah, I should have just numbered it with, let me fix that. Let's just number it here with 1. Yeah, this one we don't need. It's just 3 numbers. And so we have S1, S2, S3, S1, S2. Okay. So now that we have this third step, this is 0. And then let's make this 4 just to see more examples. Okay, snaps. And so snap 4, what happens? We have S1, S2, S3. So snap 4, a new snapper is toggled again. So all of those that are powered, so we follow our rule here, which says that when after a snap, SI, if powered, can be toggled if state can be toggled. So if SI is powered, it can be toggled. So let's look at that. So that means that here it becomes 1 because it's powered, because it's connected to S2, which is powered. Here it didn't change because it was connected to S2, which wasn't powered. And so this one, since it's powered, toggles its state to 0, 0. And this one, since it's powered, toggles its state to 0. And this one is plugged to L. If we continue here, let's continue this other way here. So on snap 5, let's adjust our example here to use 5 so we can see a lot what's going on. Maybe let's even put 6 so we can see as much as we can. So now we have S1, S2, S3 plugged to the light, and this one, each one of them is plugged to the other one. And the last state that we were in was here. So we had 0, 0, 1, so this one was powered. And these two are zeros. So what happens? That means that those who are powered get toggled. So that means we get, so S1 is powered by socket. So they are still powered but toggled off. So that means that this one becomes 1, this becomes 0, and this one becomes 1, this one becomes 1. So this is like the second one, which toggles both snapper and then cuts powers from the second one, like those. And then if you go to snap, you can continue, but you can find out that, like in the last case, where the light would be on, is only when all of them are powered, because for that S3 would be receiving power, the last one would be receiving power, and L would be on. So the realization of this is the following: is that so it's that the number of states that like the light is on only if the number of states from 0 to 1 for the snappers let's word this differently so that it can be better understood. So what we want from the answer, like the question that problem asks is for each is how many clicks or how many snaps are needed to make the state, to make the lights on. And we said that the light would be on if all of them become 1, set to 1. So that means that what we are looking for is how many snaps needed to make state for all from 0 to 1 is 1. Okay, and this here is equivalent to the following. That is actually equivalent to having, so the number of these state, like the number of this state of these snaps, like the number of permutation that you can get is 2 to the power of n minus 1. We can verify this easily. So for n equal to 2, that means we would have 4 minus 1, which is 3 states, which is correct because we can have 0, 0, 0, 1. This one is not. So we would have 1, 0 and 1, 1. And same thing for the other states. And here it's when the light becomes on. Actually, sorry, it's 4 times. But this one is the initial step, so we don't need to count it. Yeah. So how can we calculate this? An easy way we can do this is just by saying, by representing like the k value. So if you get, like, say in the problem we got k equal to 47 and n equal to 4. So to know how many steps are needed or how many snaps are needed to get to, like, k bits on, then we can just do the following. So 47 in bits is 1, 0, 1, 1, 1, 1, and n, like, is equal to 4. So we just want, so the key idea is we want the number of snappers, to each have state on. So we want each snap to have state on. So for n equal to 4, we want 4 snappers to be on. for n equal to 3, we want 3 snappers to be on, which means we want these to be 4 bits to be on. So we can do this, and we can just end this, do an end operation, bitwise operation, and we can get the value like that we want. We can know if it's on and off by, so if we do the end operation here, we can have 1 1 1 0 0. And so what we want is just that all of these are on, so that the light that is plugged into it can be turned on. So that means what we want is that the result has n bits on, and that's the case here. So we can just say that light is on. For the other case in the set, in the example, let's take a look. So if we have a case where n is equal to 4 and k is equal to 0, that means we have k equal to 0, so let's represent that in binary. 0 0 0 0 0 0, and that's k, and n is like 4, so 0 0, so we want 4 bits set, and so here 0 0 0 0 0 0, so all of them are 0. That means our light here would be certainly off, so we can directly return off. So we can do this operation really easily by just doing bitwise operations. Okay, so let's take a look at this. So the key realization here that I want to emphasize is that the answer, or the light, is on only in this case. The light is on if and only if the rightmost n bits, which n is the number of snappers, of k, which is the number of snaps, is set or are set to 1. This is the main realization that will allow us to solve this problem. And from there, everything else can be just optimizations for how to manipulate bits, and just getting used to and just figuring out how to solve it. I will code this probably in both Haskell and Java or Python, and you can take a look at that. It would be either in this video or in a separate one. If it is in a separate one, I will add the link. Okay, so let me just give you a general idea of the implementation and how it would look like. So what did we say here? It should be that the rightmost n bits of k are set to 1. So we can just figure out how to calculate that, and that would be just doing k and ending it with a value of some value a, and checking if that equals to a, which is having a is just having the k bits, like the n bits set, which is what we did here. So a is just this value here. And so how can we calculate this a? So a, in order to get these ones like n bits, we can just make it to be 2 to the power of n minus 1. And so we need only to check if k and a is equal to a. That means the light is on. If not, that means the light is off. So this is if it's true, can be true or false, so that means on, light is on, and if it's false, that means the light is off. And we can try this on a bunch of examples. So if you look at this, a equal to a. So let's try this on the examples that are given in the problem. So we already tried it on 447. So if we try it on 1 and 0, so this is k, actually this is n, and this is k. So we can just, or 0 with 1, and check if that is equal to 1, and do the same thing for 1 1, and do this. Yeah, actually for 0 we can, yeah, about that, and do it for the other example, 1 1 1, and 447. Okay, so let's do it for 447. So here k is 47 and n is 4. So that means 47 is, actually let's do a different example just so to make it simplest, to make because 47 4 we already did that one. So let's take n equal to 3, and let's take k is equal to let's say 42. So 42 is 1 0 1 0 1 0, and n3 that's like 0. So n3 that means let's have 3 bits set. So that means we have 1 1 1. So that will give us end here 0 1 0 1 0. That means we would get off. And if we try, yeah, you can try this on a bunch of examples, but it gives answers really fast. So next we will take a look at an implementation of this in both Haskell and Java or Python. Yeah, solution in Java for the explanation that we were talking about. So it's very simple. We just get as input n and k, and we create a mask which is the same as the value a that we described, which is just like a number where n bits are set in a binary form. So say if n equal to 4, it would be like it would have 4 bits set. So this is basically the same as 2 to the power of n minus 1. And what we want is, if we end k, which is the number of snap, with that, we get that same mask. So that means we have all the snappers set. So if that's the case, that means the light would be on, so we return on. Otherwise it would be off, so return off. And if we run it on these values that we had on the problem set, we can see we have on for this one and off for this one. And that's, if we take a look at CodeJam snapper problem here, so that's the case. 1 0 is on. We have a small, yeah, so 1 0 is off. Second case 1 1 should be on. So if we do the second case 1 1, should comes out as on, and the last case that we did was on, and 4 0 should be off. So 4 0 should be off. This one is on and that one should be off. Yeah, so we got the right solutions for this, and it will run really fast on a large set of inputs. So that's all for this. Yeah. Okay, so let's implement it in Haskell. So let's implement snapper chain problem from CodeJam 2010 qualification round. I explained it earlier in a video, so let's just continue here. So let's see. First, I would like to do just a simulation of the problem, like not really like an optimal solution, but more of a simulation and a brute force way, so that we can get the idea and then move from there. So first, let's define our type here, which let's call it the type of like the snapper chain that we have. So I'm choosing to represent it here just as a boolean. So let's say we would have the chain that we talked about, S1, S2, plug it to S3, and the whole thing like plug it to Sn, and then plug it to light. So I'm going to choose to present it by false, like for off, sorry, and true for on. So it would be something like this. These are the states of these snappers, and we are going to have on like be equivalent to true, sorry, and off be false. And so we start out by all of them off first. Okay, and so let's represent, so this would be just like almost an exact translation of the problem. So let's do the snap on and off when the user snaps his fingers. And so that one would take in a snapper chain. Say for example the first one where all of them are false, and then when a snap happens, it transforms it to a new one. And so first, if we have an empty list, nothing would change, we would just get an empty list. Now if we have on a list, so let's say the first element is C and then the rest, for that we would check if it's powered, then that means we can toggle it on, as the description of the problem says. So if it's powered, so if you take a look here at CodeJam 2010 snapper, this one, so it says that any snapper receiving power at the time of the snap would toggles between the on and off state, so only if it's powered. So we can check if like the rest here is powered. Then we can snap it off, so this way, snap on and off. And toggle the state of actually there seems to be an error. Let me verify. So if C is powered, then we toggle and we snap on off the rest, and we add we toggle the state of the powered value, which is the powered value of C. Else, which means C is not powered, then we don't change it. And now we need to define these other values. So is powered, how does it look like? So it gets a snapper chain. So actually C is powered only if the rest is powered. And we can just continue here, and we will return bool if it's powered, and we can continue by doing this. So if it's empty, then we know we can just return true. Here it's this, and we can here just define it recursively. So we can check in the on state, if it's in on state, this value, and check if the rest is powered. Check each one of them. And so in on state, since we are using a Boolean representation, then it would be on if it's true, and it would be off if it's false. So that's the same one as just checking true and false. So we can just use identity function. And then toggling the state is just switching the true value from either true to false or false to true. And so that would be just not, equivalent of not function. And that is all. So let's see, let's run this here. So let's say, so what does the algorithm do actually? So what should the program be? We should continue snapping multiple times. So let's say in order to continue applying a function multiple times, we can use iterate, and we want to apply snapping multiple times, and we want to apply it to a list of our values. So let's say we would have the initial state here with as many snappers as we have. Each of one of them is to false first. So let's pick just 3 snappers. So iterate continues indefinitely, so I should have did take. So let's kill this buffer here, and go back. So let's run what we wanted again, but this time make it terminate. So snap on off with 3 snappers, and take, let's say, let's take 4. Here I need to apply this to the scope. And so there you go. Now we have false, 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 the initial state, and then true, false, false, and then true, false, true, and then false, true, true. So it's so if you take 5, you can see all of them should show false, false, true. And since we have 3, let's do 8 to get to the final state. So we can see here in the last one, we get to true, 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 which means all of them are on, which is the case where the light is on. Okay, so this simulation works quite well. what we can do is just show it in binary so that we can like visualize it in the same way that we explained the problem. So if we do snapper chain, we want just to return from a snapper chain to be a string of booleans, just a string that that shows the boolean representation. So that will be taking, just mapping every value b if then 1, and else we just give 0. And so we have this. If we try to just call map show binary, you can see we start out with all zeros, and then at the end we get just ones. So that's cool. That's what we want. Now, if we wanted to like find the solution with just this here, we can say, so we get like, say we get like solve nk. What we would do is we would take n, not really n, we would take how much we would have n snaps, and so we would iterate snaps k times with that, and we would say iterate snap on off, and we can just like replicate false n times. It's to get the number of snappers here. We want to them because let's give you an intuition of that. So if you say replicate 3 false, we get false, 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 which is the result that we want. And we need to, yeah, just do that actually. That will give us probably, and we need to get the the length of that -1, of course, to get rid of the last initial step. So if we do solve for that with 447, we get 46. But our goal should be that, so that actually this is not enough. So if you take this, actually, let's just take I think last of 1, 2, 3. Yeah. So what we want is actually to take last of this. Where we want to filter by being equal to actually that would take I'll do it in a second, in a couple of minutes. Let me just first do the optimal solution that we talked about. So the optimal solution that we talked about in the explanation of this problem was that we can just check if k plus 1, which is the number of snaps, if we do like k end if we do k end 2n 2 to the power of n minus 1, that would give us the solution. And that is equivalent actually to we can just do k plus 1 mod 2 to the power of n, and check if it's equal to 0. And so first solve function would be say solve1 would be we would get n and k, and we would just check if k plus 1 mod 2 to the power of n. So this here is an infix notation. And we can just check if this equal to 0, then just show on, else show off. And if we do this on solve 447, yeah, let's define the type. Yeah, solve 1 actually. Okay, and if we do it for 1 0 off on, so this matches the result that should be here. And if we do 4 0, we get same thing. So that's good. Now let's solve it in the other way that we explained also, which is that we can just check that k and the value a is equal to a, where a is equal to 2 to the power of n minus 1, right? So that one also should be straightforward. We can just do solve 2 and k and just check that k, and we just need to import here data dumbo, and we can check that this is equal to a, and we define a as 2 to the power of n minus 1. Actually, maybe we need data depth bits too. And so here, if this is true, then we can say on, and else we can say off. And if we implement this, that's correct. That's correct too. And if we do this, should be on, and 447 should be on. Yeah. It up for snapper chain. I will probably continue doing more of these CodeJam solutions walkthroughs. So subscribe and stay tuned. Bye bye.